Now you might be wondering why we'd be showing you a large X-ray imaging centre in an engineering context. Well, there's plenty of good reason. It comes down to non-destructive testing and evaluation. Many good financial, economic reasons why I want to inspect the things that we build, but very good safety reasons as well, why I like to see inside parts in a maritime context, automotive context, aerospace context, check things that fit for purpose, defect-free.
Welcome to the mh-VIS X-ray Imaging Centre, which is home to one of the UK's largest high-energy micro-focus CT scanners, our Hutch, which I'm sat inside here. Here we do non-destructive volumetric imaging, so looking inside structures such as this carbon fibre aircraft wing section, and we can also do large metallic structures such as this.
The easiest analogy I can give is a standard light bulb. So this is our X-ray source, vacuum chamber, and inside here is a little tungsten filament, just like you'd find in a light bulb, and we're drawing electrons off that filament, accelerating them under a huge potential difference. So this gun has 225 kV, and this one has 450 kV. So the electrons get accelerated, and they smash into a target, release a lot of energy, so we get light and heat and the occasional X-ray. That's how we're generating the X-ray radiation, which flies across the room through the specimen, and we get the radiographs, which we can then build into a 3D volume. So a computed tomography scanner you may be familiar with in a hospital environment. This is very similar, but very different at the same time. One of the key differences is the resolution that we can get to. Hospital CT systems generally go down to around about 0.5 millimeter, maybe a little bit less than that. We can get down to about 3 microns. Now bear in mind, a human hair is around about 100 microns in diameter, so it's really fine resolution, and that's what's needed for some of the specimens that we look at. So once the X-rays have gone through the specimen, we then detect it over here. And this is basically a scintillator, so something that glows under X-ray radiation, and behind that is something that's like a digital camera. So we can record thousands of images of this glowing screen as the object is rotating. For every CT scan, we generate around about 32 gigabytes in a single volume. So lots of data. But sometimes we're looking at very large things, in which case we can move the detector across to one side of the room or across to the other side of the room and fuse those radiographs together. We can also do it in the vertical direction, which means we can have a detector effectively the size of the rear wall of this machine. So we can look at really large objects, but still going down to fine resolutions if we need to. So one of the things that we do with this machine a lot is in situ testing, not just taking images of something as it is, but putting a rig under here that can put it under some sort of load, either thermal or mechanical, and see how damage propagates, often to the point of final failure. Have a look inside here. See if you can guess what this is. That scale is in centimetres, and it's a rat's vertebrae. Now just a typical example, if I was to give you that and ask you to measure it, I think you might struggle. But with this sort of system, we can get both the outside and the inside geometry, which enables us to then fit a surface to it, mesh that, which can then be fed straight into a 3D printer. So this is that vertebrae, obviously blown up in scale, but all the fine detail is in here, including inside.
So when you get to your third year, you'll do an individual research project, and you might be doing a project where you come to the mh-VIS X-ray Imaging Centre for some CT scanning. So examples of projects that we've had here in the past, we've had people looking at additive manufactured components to do defect analysis. So test the distribution of cores, looked at damage evolution in carbon fibre composites, volcanic eruptions, the design and manufacture of carbon fibre hydrofoils, scanning archaeological bones for biomechanical analysis, looking at corrosion damaged reinforced concrete columns, metallic specimens such as steel, railway steel, biological specimens, composite specimens like carbon fibre or glass fibre, and many, many more.